Hi, good evening all. This is Vishal Singhal from CellStrat. Today we have Mr. Shreyas S.K from, uh, he's a deep learning researcher with CellStrat AI Lab and very expert in AI domain. He has recently got an opportunity for a US client, but now he won't be going, I am told. He's saying that I won't be going there, but he'll be shifting elsewhere. He is currently in Bangalore, but he'll be shifting, I think, to North India very soon for the same. And so, he's an expert in this domain. I suggest you ask a lot of questions to him because he is his webinars are in demand and always very liked by audience. Hope all of you are keeping safe and uh, you will get full value out of it if you ask as many questions as possible while these times are on and right time to upscale and rescale yourself. So this session is being recorded and will be made live on our CellStrat YouTube channel. I'll share the link of in a few minutes while the webinar is on. So yes, I'll transfer the controls to you.
Yeah, okay.
And we have about 50 to 55 minutes for the session and then about 5 to 10 minutes of Q&A. So let's stick to the timeline and let's go ahead with it. Okay. So over to you. Go ahead.
Okay, are you able to see my screen?
Yeah, go ahead.
Okay. Yeah, so good evening, everyone. My name is Shreyas. I'm working as a machine learning engineer in HCL Technologies. I'm also a part of CellStrat as a deep learning researcher. So today, as part of CellStrat webinars, I'll be giving a presentation on interpretable named entity recognition using LIME. I'll also show a code demo after the presentation ends. And I'll also be showing the visualizations of attention heads using BERT. It is a visualization tool that has been developed by IBM. So let's start with the presentation. So why do we need to interpret whatever the AI models that we build? So the interpretability is very important because once we are negotiating with the customer or client, he will be very interested to know how we are going to explain our AI models. So the explainability of AI models are very important for confidence building or trustworthiness of the model with the customer or client. So if the customer is not able to understand why a particular prediction is being made, then he will definitely not consider the project for deployment. So it will become very important to satisfy the customer with whatever the AI models that we build. That's where the interpretability comes into picture. So here in this presentation, I'm going to talk about named entity recognition, and I have taken a data set from Kaggle where there are around 45,000 sentences, and each and every word in the sentence has been mapped with the corresponding POS tags that is a part of speech tag, as well as the entity tag. So what is named entity recognition? So it is a process of identifying and categorizing named entities in a given text. So here the entities, as you can see in the picture, all these highlighted texts are the entities. So there are various entities such as organization, location, time, name, money, and rate. And there are many more entities which have not been mentioned over here. So here you can see Tencent has been tagged as a person. Baidu is tagged as an organization, and NORP means nationality or religious or political groups. So this Chinese and Asian have been named as NORP. 2017 as date. So there are several entities which have been named correspondingly. Microsoft, IBM, and Google have been named as organization. So this is the named entity recognition. So these are some of the other terms which we'll be using other than named entity recognition, which mean the same. Entity identification, entity extraction, and entity chunking. All these will mean the same, which is named entity recognition. So why do we want to extract the entities from any text? What is the various applications of named entity recognition where it can be actually used? These are the three applications that I have listed, but there are many more. The first one is content recommendations. So when you open a news application in your mobile app, you will be suppose if you open a particular content here from the first picture you can see 22 dead in Cola's terrorist attack. So when you're reading this particular article or content, at the bottom of this content you might observe that there are various recommendations which are similar to this particular content which you are viewing right now. So here also you can see the recommendations: witnesses stories from Manchester attack, evil loser Trump. So these are the various recommendations that the application is giving to you when you are reading this particular content. So these are the content recommendations. The content recommendations that, are also given based on the named entities. So for all the news articles, the named entities have been made, and based on the particular content that you are viewing right now, the named entities have been recommended based on the content recommendations. The second one is classifying content for news articles. So in news articles, you will be having a lot of categories such as sports, politics, jokes, or international affairs, or many more. So to classify the content based on each of these categories, named entity recognition is used. And the third one is customer support. So here you can observe a customer has used Twitter to report the problem that he is facing with the product. So here you can see based on the Chroma retail store, he has reported a particular content at Bandra location based on the Fitbit item that he has purchased from Chroma retail. Suppose Chroma Retail has to deal with the problems that the customers are facing overall the world, and many of the customers would have used Twitter to express their problems. So they will use named entity recognition to find out at which particular location a particular tweet has been made and for which particular product. So when NER is done for this particular tweet, it will extract Bandra and Fitbit. So based on these entities, they can actually categorize based on the location, and they can send these tweets to that particular location's customer support. And there are many more applications other than this also. So NER entities and IOB tagging. So the right now the dataset that I have used for this presentation, it has these entities named, which is a geographical entity, organization, person, geopolitical entity, time, artifact, event, and natural phenomenon. So I'm supposed to predict which particular entity a particular word corresponds to based on the context. And these are the IOB tags that have been attached to these entities. So the IOB tags are the inside, outside, and beginning of a particular entity. So this is a common tagging format for tagging the tokens. So I corresponds to the prefix before a tag indicates that the tag is inside a chunk. B prefix is before a tag indicates that the tag is the beginning of a chunk. And O represents that a token belongs to no chunk, that is outside of a chunk. So here chunk refers to any of these entities. So if a particular word is at inside a particular entity, it will be named as hyphen geo. And if it is at the beginning of a particular entity, it will be named as b hyphen person, similar to that. So to deal with this data set, I have used bidirectional LSTM with default embeddings, as well as bidirectional LSTM with Elmo embeddings, which is a contextual embedding. And after that, I have also used BERT to extract named entity recognition. So the first one is a bidirectional LSTM with Elmo embeddings. So here we can see it is different from traditional word embeddings because Elmo is a contextual word embedding. So based on the context, a particular word can have different embeddings. So in the diagram, you can observe the cat is happy. So the first layer is a bidirectional LSTM, and second layer is also a bidirectional LSTM. So for the first layer, the input representation is sent, and the output that we get from the first layer of LSTM is sent as the input to the second layer LSTM. And for the second layer LSTM, you can also see the input representation as well as the output representation of the first LSTM is being sent. So the Elmo embedding for a particular word is a combination of second hidden state, first hidden state, as well as the input representation of the particular word. So the function f is a weighted average, not exactly the weighted average. It will depend on which task we are dealing with. For sentiment classification, it will give a different Elmo embedding. For NER, it might give a different Elmo embedding. So the function f is based on the task that we are dealing with. So after this Elmo embedding is found out, these are sent as the inputs to the bidirectional LSTM in order to get the output as the named entity recognition, named entities. So here you can see each of these Elmo embeddings are sent to the bidirectional LSTM. This is a forward LSTM and this is the backward LSTM. And the output that we get from the bidirectional LSTMs is the entities. So the higher level layers capture context dependent aspects of word embedding. Lower level layers capture model aspects of the syntax. Elmo produced multiple word embeddings per single word for different scenarios. This one I said before. So the Elmo embeddings are very powerful when compared to the glove embeddings, which are not contextual embeddings, but they are static embeddings. So the model performance that I have obtained just by using bidirectional LSTM with the default embeddings is this one. So the loss for the training set is 0.0534 and for the testing set is 0.0585 and the accuracy is 98.33 and 98.27 for the training and testing sets accordingly. And you can see the curves have been converged very well for both accuracy as well as the loss. So this will be a multi-class classification problem. So there are totally 17 outputs that can be predicted, 17 unique outputs. So I have used a categorical cross entropy as the loss function. So when I replace the default embeddings with the Elmo contextual embeddings, this is a performance you can observe. Here the loss has been converged well with respect to the default embeddings. Here you can see the loss is 0.0534 and here it is 0.02. And even the accuracy 99.06 and 98.67. It has improved with respect to the default embeddings, which is 98.27 to 67. So coming to the BERT architecture, so BERT is a pre-trained model that has been built for various downstream tasks. So the BERT, how the way the BERT has been trained is based on the masked language model as well as next sentence predictions. So once this pre-trained model is available, whether it may be, you can use BERT uncased or BERT cased or BERT large, whichever model you want. So based on the complexity, you might use different models. So this BERT can be used for various downstream tasks, such as sentiment classification or entity recognition, or even question answering dataset, that is SQUAD. So for this pre-trained model, once you attach a dense layer, we have to fine tune the dense layer, and the output that we get from the dense layer will be based on the downstream task that we are dealing with. So in this slide, I will be comparing these two pictures. So here you can see initially this is a sentence, I am fine, and it has been the CLS and CP tokens have been embedded to this sentence. So for each of the word in the sentence, an embedding has been constructed. So the embedding's dimension is 768. So for each and every word, there will be 768 columns. That is one row and 768 columns. That is the dimension of each and every word. So once these input embeddings have been constructed, they have been they are projected linearly onto the key, query, and values. So these key QKV are used in order to calculate the self-attention heads. So I'll come to this diagram. Here you can see Q, K, V are the vectors. That is a query, key, and value. Usually K and V vectors are the same. So to compare the query vector with the value vector, we will be finding out the similarity between the Q and V in order to find out how much attention we have to pay. So this is a multi-head attention. This is how the scale dot product attention is calculated between Q, K, and V values. After this, the scale dot product attention has been calculated for multiple layers. Because this is a multi-headed attention, we will be having multiple layers of self-attention. So here you can see V, K, and Q values have been linearly projected. Here you can see the linearly projected layers of Q, K, and V values. And here you can see 64 is the dimension of each of these key, Q, and values vectors. So what is the why do we get 64 as a dimension? Because here we are seeing the each word is represented as a 768 dimensional vector, and here it has been sliced it down to 64. Why do we do this? This is because when we are not using multi-headed attention, and if we suppose assume that we are using self-attention instead of multi-headed attention, then the dimension of each of these key query and value vectors will be the same as the input embedding, that is 768. In multi-headed attention, we are having multiple layers of self-attention. So what is the advantage of this? Suppose we are using only self-attention, then the features that the BERT captures from a particular word will be very less. In multi-headed attention, we are having multiple layers of self-attention. Therefore, we are able to capture many features for a particular word. So here you can see 768. So from the BERT's architecture, we all know this is the encoder-decoder architecture of the BERT, and there are 12 layers of this transformer model, encoder-decoder, in the transformer model. So there are 12 layers of the same architecture in BERT uncased model. Therefore, this 768 dimension has been divided by 12. That is, this input embedding 768 has been equally distributed among all the attention heads. So there are 12 layers of this encoder decoder architecture. Therefore, 768 divided by 12, you will be getting 64. So each of these 64 dimensional vectors are sent to the attention heads. I have a question. No. Okay. So each of these 64 dimensional reduced representations are sent onto the attention heads. Since we are having 12 attention heads, you can see here there are 12 attention heads. And we are able to capture many more features because of these many number of attention heads. After this, whatever the attention that has been captured from these multi-headed attentions, they are further projected to the feed forward layer, and further it will go to the decoder part. Here we will be dealing with the linear and softmax layers in order to output the probabilities. Yeah. So BERT for named entity recognition. Here, as I have discussed in the previous slide, you can see each of the a particular sentence will be having token embeddings as well as the positional embeddings as well as the sentence embeddings. All of these are sent to the 12 layer of transformer encoder decoder architecture, and finally based on the dense layer that we uh, uh, based on the dense layer that we put at the last layer, we'll be getting the accordingly we'll be getting the entities based on the downstream
So
task that we are dealing with.
here there are three questions, please.
Okay.
Please explain 768 to
768 to
64.
64. Okay. uh, I'm not oh, the computer has hanged.
Try right clicking and clicking on previous.
Yeah, I'm doing that. It's not going.
Are you able to go to next?
No, even escape is not working.
Okay, can you go to next slide?
No, I'm not going able to go either of them. Uh,
Try restarting
yeah,
the.
wait. Yeah, okay. So 768 is the input embedding dimension. This 768 input embedding dimension has been equally distributed among all these attention heads. So there are 12 layers of this transformer encoder decoder architecture, right, in BERT. For all these 12 layers, this 768 dimension has been equally distributed. You can calculate 768 divided by 12. So you'll be getting 64. So this 64 is a smaller representation of this 768 dimension. Each of these smaller representations are the key, query, and value vectors. So these vectors with smaller representations have been used to calculate the self-attention heads. Each of these attention heads will be capturing a particular feature. So these features I will be showing in the further slides, what features these attention heads will be capturing. So I'll discuss in the further slides, so you'll be able to recognize what I'm saying. So the next question is, what exactly are these K, Q, and V vectors with example of a sentence? Okay. So the keys, queries, and value vectors, in order to calculate the attention, we have, suppose I have these three words in my sentence, I, am, and fine. So if I want to calculate how much attention I have to pay with respect to I and fine, I have to calculate the dot product of Q, K, and V vectors. Suppose Q vector is a query vector. So the query vector is I. So I have to calculate what is the attention I need to pay on fine with respect to the word I. So here, if Q is the vector, the input embedding I, then key and value vectors will be that of fine. So whatever the input embedding that we get for fine, it will be the reduced dimensions, that is 64, right? So for 768 dimensions, we will be having the input embedding for fine. So for 64 dimensions, in the first self-attention head, we'll be calculating what is the degree of attention that I have to pay for the word I with respect to the word fine. So usually the representations K and V will be the same because the key and value vectors both are the same. The query vector will be the different one. That's all right. Okay.
So go ahead.
Yeah. Again, it has stuck.
I hope you didn't take your laptop out today.
No, I was using continuously. I don't know why it has happened.
Another question, related question.
Yeah.
So any example when K and V are different?
K and V. No, usually K and V will be the same because here we are dealing with two words at a time, right? To calculate the attention. So the query vector will be at a time only one particular word, and the value vector will be the another word on which the attention is being calculated. So right now, to calculate the attention at a particular instant, we will be taking care of only two words. So one is a query vector, and another one is the value vector. So we need to find out how much attention we have to pay for a particular word with respect to the other word. Still it is not. Yeah. Okay. I think I'll explain like this only. So as I was discussing before, you can see for a particular pre-trained BERT model that we use, we'll be adding a untrained dense layer of neurons, and we'll train the layer for any particular downstream task based on the classification or entity extraction or the question answering dataset. Yeah, so this is where I'm going to discuss the visualization of attention heads. So here I'll be showing what are the patterns this BERT multi-headed attention will capture, and why it is important to us. So here we can see BERT's attention patterns. There are three such important patterns that that the attention heads will capture. The first one is delimiter focused attention patterns. Here what it does is the attention head focuses on the SEP tokens when it can't find anything else in the input sentence to focus on. So I'll also show you the how this works. The second one is a bag of words attention patterns. Here the attention is divided fairly evenly across all the words in the same sentence. The third one is a next word attention pattern. Here the attention is focused on the next word in the input sequence except at the SEP and CLS tokens. So in this diagram, you can see for whatever the sentence you have to find out the visualizations of the multi-headed attention, you can input over here and update, and you can decide whether you have to include the multi-headed attention calculated for special tokens, that is the CLS or SEP tokens. And this is a degree of attention, that is 70% of attention. If you want to focus on, you can toggle it over here. So this is a layer. I think it will be better. I'll explain in the, yeah. So here I have taken this sentence. I went to the store. At the store, I bought fresh strawberries. So this is a visualization that I have got. This is a multi-headed attentions visualization. Here you can select, there are totally 12 layers of encoder decoder architecture, right? So you can select whichever layer you want and visualize the multi-headed attention. So there are 12 layers, and in each layer there are 12 heads. So each of these heads are self-attention heads only. So we have multiple self-attention heads. So based on the slide, I'll be showing you the patterns. So here you can see, based on the slide, here you can see delimiter focused attention pattern. So as I discussed here, attention it focuses only on the SEP tokens when it can't find anything else in the input sentence. So here you can see each and every word is focusing on the SEP token. So the next one is bag of words attention patterns. Okay. Yeah, this is a bag of words attention pattern. So here you can see 10, 9, yeah. No, this is not the one. Okay. So this is a pattern at attention head 9. We are getting this bag of words pattern. Here you can see each and every word is focusing on a cluster of words which are nearby to it. The third one is a next word attention pattern. 7. Yeah, here you can see the clear pattern. This is the next word attention pattern. Here each and every word is focusing on the next word. So similarly, these are the kind of features that the multi-headed attention will capture. So here you can actually find out what is the importance of using multi-headed attention instead of only self-attention. In multi-headed attention, we are having 12 layers of 12 heads of multi-headed self-attention. Therefore, each of these self-attention will be finding out one or the other feature for a particular word. So suppose if you are using only self-attention instead of these 12 layers of self-attention, you'll be capturing only one feature. So instead of capturing only one feature, you are capturing 12 features based on each of these multi-headed attention. So coming to the interpretability, I have used a Lime library to interpret the models. So whatever as a name itself, it is mentioned that it is local. What does this mean? It is locally interpretable. What does this mean? Here, suppose this is the AI model that we have built, and this is a complex optimizing function. Here you can see it is very non-linear. So this is the optimizing function that has been built by the AI model. When we want to interpret a particular example, it will be only satisfying the local conditions. It will not be satisfying the global conditions, because suppose I have optimized my AI model for around 30,000 sentences. So this is the complex nonlinear function that we have obtained. So the local interpretable model will be building a white box model that I'll be discussing further. So this white box model will just have to satisfy this linear line. So this is a linear classification line that you can observe. For simple models like a logistic regression and all, we'll be classifying the data set based on the two classes, right? So here you can see, suppose a plus is one class and these circles are another class. So locally, we are able to separate this plus and the circles. So this is what the local interpretable model agnostic explanations the Lime library uses. So this is a procedure that we follow usually in order to interpret a particular sentence. Initially, we'll be generating a fake data set for the example that we have to explain. After that, we'll use the black box estimator. So this black box estimator will be the bidirectional LSTM or the BERT model that we have used. So we'll use this model to get the class probabilities for each example in the generated dataset. The next one is we'll train a new white box estimator using the generated fake samples and the labels. So once we have trained the white box estimator, we'll explain the original sample with respect to the weights that have been trained by the white box estimator. The prediction quality of the white box classifier shows how well it is able to approximate black box classifier. So this will be clear to you once I show you the code demo also. So the text explainer library has been used in order to find out the importance that we pay for each and every sentence in order to give the predictions. So initially we will be generating 5,000. This is a default number and it can be tuned. Initially there will be 5,000 fake samples that we will be generating from the original data sample. After that, The white box model is trained using the SGD classifier. So SGD classifier is a linear model plus the stochastic gradient descent optimizer. So there is a difference between SGD classifier and the logistic regression classifier. So logistic regression, it will be generally using the gradient descent optimizer, but here the SGD classifier will use the stochastic gradient descent optimizer. So this is the default white box model the text explainer library uses, and you can also change different white box models to maybe SVM can also be used. And the features that this SGT classifier will be trained on will be based on the bag of words or the bag of words for bigram models. So whatever the data set, whatever the sample that we need to get the explanations, we'll be initially vectorizing it by using bag of words or bigrams or n-grams. And by after we obtain those features, we'll be training the classifier. That is a white box model. After that, so as I said you before, we can use other alternative algorithms. So instead of SGD classifier, we can also use decision trees and character level n-gram features, and even different vectorizer can be used. So here I have used a count vectorizer. Suppose for bag of words, we'll be using count vectorizer in Python. So instead of using count vectorizer, we can also use hashing vectorizer or different forms of vectorizer. So the loss function for this is KL divergence. KL divergence is used as a loss function to measure how well the probabilities are being approximated for the white box model. Accuracy is weighted with cosine similarity to find out the similarity between the predicted as well as the original samples. So I think I'll show, this will be clear to you once I show the code demo. Yeah. So as you can see, there are around 47,000 sentences. I think I have a question. No, text explainer library comes within Lime. So Lime is a tool. So in Lime, there are different libraries for different domains. Text to explain the interpretability of a particular text, we'll be using text explainer library. So we can also interpret a classification problem or a regression problem, whichever to interpret. We can interpret according to the different libraries provided by Lime or Elify. So as you can see here, there are around 47,000 sentences in the data set. And for each and every word in the particular sentence, the POS that is a part of speech, as well as tags have been mentioned. No, the code is not available in GitHub, but I will share it once this presentation is finished. So initially from the data set, you can see each and every word has been separated with different IDs. I've merged all these IDs with respect to the sentences. I have used a group by. So as I said you before, there are totally 17 different kind of labels. So here you can see a geographical location, B, I, and O are the IOB tags that we insert before a particular entity. So in the vocabulary, there are totally 35,170 unique words from all these 45,000 sentences. And these are the building sequences of sentences, labels, and post padding. I have used a post padding to get the uniform length of each and every sentence. Training and testing split, 10% is the testing data. So this is a bidirectional LSTM with a default embeddings. I have not used contextual embeddings over here. And I've already shown you this diagram. So when it comes to the explainability of a particular model, we can see here. Okay, this is the black box model that I have already built. From this code, you can see I have I have built a separate class for the black box model, and this predict function will be giving the black box model's predictions for a particular word. So suppose if I want to give the explainability for a particular sentence, so I have chosen 46 as the index. So this is the sentence corresponding to the index, and these are the labels attached to the each and every word corresponding to the sentence. So here this is a sentence, and these are the labels that a particular word follows. So you can see side by the labels as well as the word. So this is the sentence that I'll be using to explain the model. So based on the workflow, I have explained you that we'll be generating fake samples. So here a masking text sampler is used to generate the fake samples. So we'll be masking different words in a particular sentence. So the different words that have been masked are replaced by unknown token. So just for an example, I have sampled this particular sentence into 4 different samples. These are the 4 different masked samples. Here you can see the masked words are replaced by unknown token. And there are 4 such samples that have been generated from the original sample. And you can see the similarity of these masked samples with respect to the original sample. It is showing the similarity between 70% to 80%. So in order to train the white box model, so as I said you, SGD classifier is the white box model that I'll be training with. So what is the input data that I'll give to train the white box model? So the input data that I'll be giving to train this white box model will be the fake samples that I have generated. So here, just for an example, I have showed you the 4 samples that have been generated, but by default, there will be 5,000 masked samples similar to these. So here you can see 5,000 masked samples can be generated, and you can vary this number. More the number of samples you will generate, more better the white box model will be trained for. So I have used the masked sampler. Here you can see the sampler, masked sampler, and number of samples. And I have fit the original sample text with respect to the black box predictions. Here pass the original text sample and black box classifier function, which gives probabilities to fit the function. So I'm explaining the predictions based on the white box models, weights and biases. So here I'm anyways training the SGD classifier, which is you can compare it to similar to the logistic regression. So I'll be having a lot of neurons, and I want to optimize the weights and biases of these neurons. Whatever the weights and biases that I get for this logistic regression or the white box model, those weights I'll be using in order to explain the predictions made by the black box model. So this sentence you can focus on. White box model will predict the outputs of black box model. It will not, the white box model that we train, it will not predict the 2 labels. It will predict only the outputs of the black box model. Only then we will be able to tell how good our black box model is. So here I am explaining this particular word California. So the particular California word, the target label is IGO, so inside geographical location. So I want to explain why this word California has been named labeled into IGO. So this is the explanation the text explainer has given to me. Here you can see the contribution and the feature. So the highlighted text, which is in green, it is showing positive importance in order to predict the word California as IGO inside the geographical location. So here the score 0.844 is the sum of this contribution. You can see 2.893 minus 2.049. It will lead to the score 0.844. So this is the prediction that has been made. But as I said you before, this is a multi-class classification problem, and I have 17 such unique labels. But here I have selected only the top 5 target labels for the explainability. So you can see the word California is being predicted at 0.672 probability, and similarly the word California is being predicted at 0.27 probability for inside the organization label. Similarly, at this probability for beginning of the geographical location label. So for each of these labels, we are getting the what is the probability that a particular label can be named for a particular word. So only for true predictions, we will be getting the score more than a positive number. You can see for false predictions and all, the score is in negative. And these colors, green will represent the positive influence, and this light brown will represent the negative influence. So as I said to you before, this is the metrics that I have obtained for the white box classifier. The KL divergence is 0.02. So the KL divergence, what it does, it will approximate how well the predictions have been made for the generated as well as the original sample. So if the generated and the original samples probability distributions are very similar, then the KL divergence will be very low. This is what we want to achieve. And even the score, so here the score is the accuracy score weighted by the cosine distance between generated and original sample. So here the accuracy is also very high for the white box model. So these are the default number of samples. As I said you, T is the instance of the text explainer. And for example, as I said you, these are the 5,000 fake samples, and out of them I have just sliced out the first 10 fake samples that have been generated to train the white box classifier. Here you can see many unknown tokens which have been masked. So the vectorizer that has been used to train this white box model is a single document vectorizer, and this is the SGD classifier that has been used to train the white box model. So question is, which is a better pre-trained model for NER, BERT or ELMO or anything else? So the state of the art says we'll be using BERT because BERT is a very deep encoder decoder architecture, because we are having 12 layers of transformer architectures in BERT. But when you use ELMO is just a contextual embedding that you give. So BERT is used to for various downstream tasks that I have mentioned before, for sentiment classification or NER or squad. But ELMO can't be used to for any of these downstream tasks. ELMO is just a contextual embedding. Can use GPT-2 model instead of text sampler. No, text sampler is to generate the fake samples to train the white box model. So the white box model, what we do is for the generated fake samples, we are finding out the optimized weights and biases. So these weights and biases are being used to predict the outputs of the black box model. Yeah, that's it. So when I used ELMO, I have already shown you the performance of ELMO model. Here I just wanted to discuss how we are obtaining the parameters. So here you can see while training the model, we'll be initializing the number of parameters for embedding layer and bidirectional layer and time distributed layers. So here you see very big numbers of the number of parameters. So I just want to discuss how we are obtaining this number of parameters. So here you can see the embedding parameters. There are totally this large number. So we are obtaining these number of parameters because there are totally 35,180 unique words in our vocabulary. Okay, so for each and every word is represented as a 3072 dimensional vector. So Elmo embeddings will be getting as a 3072 dimensional vectors. So when you multiply each and every word with this dimension, we'll be getting these number of parameters. Similarly, bidirectional LSTM's parameters, here you can see, this is a bidirectional LSTM with 512 hidden units in each direction. So 50 is the maximum length of a particular sentence. So this is a formula to calculate the number of parameters in a bidirectional LSTM. So based on this formula, so since this is a bidirectional LSTM, there will be two unidirectional LSTMs, right? That's why it is 2. And the number of neural networks in an LSTM cell. So in an LSTM cell, we'll be having 4 gates: forget gate, input gate, output gate, and the cell state. So for all these gates, we'll be having many number of parameters. So that's why 4 neural networks. Input size is 3072. That is the embedding dimension of a particular word. And 512 is the hidden states of a particular LSTM. So here I'm using 512 hidden states in for a unidirectional LSTM. Therefore, it will be 512. And this is the number of parameters that we get for the bidirectional LSTM. Similarly, for time distributed layer, this 1024, when you multiply it by 17, you will be getting this 17,425. So 1024 is the input dimension, and 17 is the number of dense layers that we have added in times distributed layer. Therefore, 1024 into 17, you will be getting 17,408. Plus, you will be adding 17 biases. Therefore, you will be getting 17,425. And I just want to mention these two. That is a spatial dropout and normal dropout. So in the model that has been built, I have used a spatial dropout, which will be the correct implementation. So the spatial dropout is constructed soon after the embedding layer. So what is the purpose of using spatial dropout instead of normal dropout? Because so here you can see this. Suppose this is a particular sentence and this is the embedding dimension. If you use dropout, randomly it will be dropping out particular representations of a sentence. But when you use a spatial dropout, suppose this is the embedding dimension, which is 5 for the word the, you will be dropping out the complete representation in a particular dimension for all these words. So this is very important when we are using embeddings, word embeddings in text. And I also wanted to discuss what is a time distributed layer. Let me show the spatial dropout and actual dropout. Okay. So suppose I have taken an array which is having, yeah, Vishal, go ahead.
So what is time distributed layer?
Yeah, I'll explain further.
And there is another one. Can we use XGBoost or tree-based algos in place of SGD classifier?
Yeah, decision tree algorithms can be used for the text explainer, but only simple models will be used, not the XGBoost kind of algorithms, because this is a white box model that we want to explain. And again, we don't want to optimize a various number of parameters. So a simple decision tree kind of algorithm will be using, not XGBoost. Anyways, it is also a variant of decision tree, but a simple model will be used. Okay, so I'm showing you the difference between dropout and spatial dropout 1D. Here I have taken an array of numbers from 0 to 34, and when I use normal dropout at 0.5 dropout rate, you can see 50%, that is totally 35 elements are there, right? Or out of these 35 elements, 50%, that is 17 elements are made zeros. So it will be done in a random fashion. Suppose I use a spatial dropout in vertical direction. There are 5 columns, and 50% of these 5 columns will be 2.5. Therefore, 2 columns have been made zeros in vertical direction. Similarly, when you use spatial dropout in horizontal direction, then you can see there are totally 7 rows. So 50% of these 7 rows will be 3.5. Therefore, you can see around 3 rows have been made zeros in the horizontal direction. So the time distributed layer. So what is the importance of a time distributed layer, and where it has to be used? So time distributed layer applies same dense layer to every time step of a LSTM cell. So why do we use this? Because in many to one architecture, suppose this is a classification problem, that is why this is many to one. So based on a sequence, if we are supposed to predict whether that is a positive or a negative review, so there will therefore we'll be having only one cell that is at the output. It is not a sequence to sequence, it is many to one. Therefore, if I use only one dense layer to get the output, I have to train the weights and biases of that one particular dense layer. Suppose my task is many to many. So this is a sequence to sequence model. So when I'm using sequence to sequence model, I'll be having a lot of dense layers based on the sequence. So when there are many dense layers, individually you have to train the weights and biases for each and every dense layer. So you'll be having a lot of parameters when you use the dense layer in such tasks, many to many. So in these cases, what we do is we'll be using a time distributed dense layer. What it does is it will apply the same dense layer to each and every time step of the LSTM cell. That means it will apply the same weights and biases that has been applied for the first sequence, so that we'll be getting a lesser number of parameters. Therefore, you can compare, even in this instance, we'll be getting the same number of parameters for weights and biases. Even in many to many, we'll be getting the same number of parameters, that is weights and biases, only because we are using time distributed dense layers. So the error function is between the predicted and the actual label sequence. When you put the return sequences is equal to false, it will apply the dense layer only in the last LSTM cell. As I have said, in this many to one, you can see for the classification task, you will not return the sequences for each and every cell, right? Therefore, you will get the dense layer only at the last LSTM cell. So when you put return sequences is equal to true, so it will become a many to many sequence to sequence problem, and for each and every dense layer you will be getting an output. So that problem that I was dealing with, that is NER, it is a sequence to sequence problem. For every particular word in a sequence, you are supposed to predict what is the tag attached to that particular word. Therefore, I have used a time distributed layer. So here you can see, after this bidirectional LSTM, I have used a time distributed dense layer instead of a normal dense layer. If I had used a normal dense layer, I would have got a lot of parameters. Since I have used only the time distributed dense layer, I'm getting a very less number of parameters. I have also used BERT for this problem. Since the time is very less, I'll just show you the output. So this is the explanation of, so in the BERT model, you can see the BERT model is having 201 different named parameters. So this is the embedding layer and first transformer layer. And similarly to this first transformer layer, there will be 12 transformer layers. After these 12 transformer layers, we'll be having an output layer. And you can see here 28,996. These are the number of unique words in the training data, and 768 is the embedding dimension. And we'll be attaching the positional embeddings, token embeddings. After that, we are having the weights and biases of the normalized layer. Similarly, here also you can see the weights and biases attached to these query, key, and value vectors that I have discussed before. I will just show you the result. Yeah. So here you can see the average F1 score that is obtained is 0.83 for the testing data. Because I have a very less number of samples for artifacts, events, and NAT, I'm getting very less F1 score. Another one is BERT attention. So BERT's attention head view, even in the Jupyter notebook, it is available, but it is not so interactive when compared to the XBERT's visualization tool. So here you can actually check out what are the patterns in each of these multi-headed attention, and you can vary all these things, sentence, everything. But the BERT attention head view that is inbuilt in Python, it is not so interactive. Yeah. Okay, that's it. You can ask any questions if you have.
So audience, this is the final time for you to ask questions, although there have been quite a few asked. And as mentioned, this recording will be available in 2-3 days time on our CellStrat YouTube channel. Shreyas is a regular presenter, so you can see his videos before this session as well on YouTube. And people are asking for you to share your notebook. Yes.
Yeah. Okay, I will share it.
So once we post the video, you will be able to see the video, the notebook link most likely below that. And any other questions? So I'm not seeing any more questions. So Shreyas, would you like to share your contact details just in case, or you would like us to moderate the questions if any come in?
Okay. Shall I provide my mail ID or?
You can put it on this last slide itself if you want.
Okay.
One question has come. Meanwhile, why do we have to use white box and black box models?
No, white box models are used to explain the black box model that you have already built. So the black box model, it will be very complex. As I have already shown in a different slide. Yeah, in this diagram you can see the black box model that you build. The loss function is very complex. It is very complex non-linear function. So it is impossible to explain these black box models. That is why it is named as black box, right? Therefore, in to satisfy the customers, we want to explain the black box models. That is why we use the white box models in order to explain the black box models. White box models are a similar, very, very simple kind of models. They are not non-linear. They are very linear models. So these linear models are used to approximate based on the local context, not for the entire global context. They are approximating only they are approximating linearly based on the local optimizations.
I've shared Shreyas' email on chat for you all to contact him if you want to speak to him. And since no more questions are coming, I would like to thank you all for joining the webinar and for sparing time to listen to him as well as ask questions. So look forward to see you in future webinars, and Shreyas, look forward to more such sessions with you.
Okay, thank you.
Thank you. Good night all.